So there's a good reason I left this one to last. It is a little tricky. We're going to keep on going. So we've got this function where we've encoded our polynomial here, and we've wrapped it in traced. So like I showed, we can run the function as per normal, and you notice that we can trace up or trace down, and that acts as you'd expect. And so let's write a query which can estimate the quote-unquote derivative at a single position. Well, that doesn't make sense, right? We're just going to estimate the slope at a single position, okay? We don't want to worry about doing the derivative of the whole function. Let's just do it once, in one spot. So this should really say estimate slope. It takes our function, our traced function here, which outputs doubles, and it outputs a double, which is an estimate of the slope at the current implicit position of our comonad. So that's going to start off at 0, but it can do it at any position in reality. So here's our function. We're going to pass in this w, which represents the entire function, not just the x argument, right? So this is our f function. Maybe I should have called it f. And we can look one to the left by saying wherever I am, I don't know where that is, but I want to get the value that's one to the left by tracing our w. Now, because we're not extending, this will extract the y, which is one to the left of our current x. And we can look one to the right. So we can say trace 1. We're going to go one to the right. And just like our fancy formula, we're going to take the right y and the left y, subtract them, divide by 2, and this is our slope formula. Okay, so this is a very rough estimation, right? We're doing very large amounts. These are doubles, so you could scale these down arbitrarily, but this is, you get the idea. Okay, questions about this? This should make the slope, yeah? Okay, cool. More do notation abuse. If you don't like this, look away. I've warned you. So we're passing in the w. We can replace that with a do, and we can implicitly just trace left or right. Now remember, these aren't mutating the context. These are run on the same context. Every query happens on the context that's being passed in. So we can look one to the left, one to the right, and then of course we can just return our slope. Okay. So if we estimate this derivative, so if we estimate the slope at every position, we estimate the whole derivative function, right? If we know the slope at any given position, we've computed the derivative of our original function. That's kind of the definition. So we can write derive just by estimating the slope at every single spot. And the way we do that is just extend it along this structure. So this is where it comes in really handy that this is just lazy and this is a function. It just creates a new function. It's a traced comonad, which is the derivative. Any questions on this? A little bit of magic? No? Cool. This is cool, right? I think so. Okay. So we're going to pivot a little bit and just look at a little helper here that's going to help us continue. There's another type class in the Comonad library called apply, or Comonad apply, I think. And it has this lift w2 method. Okay? This looks really familiar to lift a2, which is from applicative. And it turns out it actually does the same thing, but certain comonads are not applicatives, and so they have slightly different semantics. But if your type is both applicative and comonad apply, then they must be equal. Okay? But we can usually think of it as a zip-like operation. So it will usually, if we have this idea of a position in our comonad, it will run the function through, like, of this spot with the value at this spot. Or if we, for instance, do lift w2 of the tupling function, it'll just act like a zip. It's a little confusing, but for a stream, it will just pair up the elements of the stream one by one, all the way down. It does what you'd expect. Cool, has this signature, looks exactly the same as lift a2. Takes a function, lifts it into a comonad. Okay, like I said, if the comonad is also applicative, then they must be equal. And so what we can do is we can actually say, well, we've got our original function, and we've got the derivative of this function. What happens if we zip the result, the y's of our original function with the derivatives at that position. Well, then we actually get a function from an x to both the y at that position and the derivative of that function and that result. And that's kind of just a cool thing that we can do. So we can actually run this at 0, and we can see, well, the y at 0 is -16, and the slope at 0 is estimated to be 0. So we actually did a pretty good job. The tangent of this line here is just going to be a straight line. And we can see some other examples. If we manually trace 0, we can see this is the same as extracting, right? Because 0 is the identity element. It's not going to move us at all. But if we trace 1 to the right, we can see that we actually have applied this derivative estimation at every position. So we're going to start at 0, we're going to move 1 to the right, and then we're going to see that apparently it's estimating the slope at this position to be 2. But the value is still -15. So kind of cool. We managed to zip two comonads together and combine their state and get more information as a result. Questions about how that works? Cool. And not all comonads have comonad apply, even though all monads have applicative, but not all comonads have comonad apply. I believe. Maybe fact check me on that one. Okay, let's look at another example. This is one of the trickier comonads, so we're going to go through a bunch. Anyone here play Minecraft? Yeah? Okay, so we're going to do some crafting, of course. And it's really annoying to just run around and build this thing with redstone, so we're going to build it in Haskell instead. So we're going to say that we can build a quiver and arrows and all of that stuff if we have these ingredients. So to make a quiver, you need a bow and an arrow. I know that's not how it works. That's fine. Let's just say that's like a, archer pack. Okay, so we've got an arrow and a bow. And in order to make a bow, we need some sticks and some string. And in order to make sticks, we need wood. And in order to make string, we need wool. And it kind of just flows through the diagram, yeah? So we have, in order to build one of these nodes, we have dependencies in order to fulfill that. So to get the quiver, we need everything underneath. To get just an arrow, well, we need feather, stone, sticks, and wool, and wood. Now, this wood here is a transitive dependency. It's not a dependency of building an arrow, but it is a dependency of something you need to build an arrow. Okay, that's important. Diagram relatively clear? Cool. So we can encode this. So what I'm going to say is that I'm going to encode this as a function which takes something that we want to build. We're going to just represent them as strings. And we're going to return a set of the immediate dependencies. Okay? So we saw there, okay, to build a quiver, we need an arrow and a bow. Sorry, this should be, yeah, that's right, an arrow and a bow. And in order to build an arrow, we need sticks, feathers, and stone. Apparently I missed a stone on the previous slide, that's okay. And so we've encoded all of these dependencies, but you'll notice it doesn't have the transitive dependencies. So this depends on sticks, but you see there's no wood here, okay? It's only the immediate ones. So we can wrap this idea into the traced comonad, but we should think about what our monoid is if we're going to do that. So if we leave it as a string, it's just going to, every time we trace, it's going to garble on another one of these weird things, and it's going to build up this indecipherable chunk of characters that doesn't mean anything. So in our case, we're going to say, well, I'm going to have my comonad represent the things that I want to build. Okay? A set of all of the things that I want to build. So we're going to accept a set as an argument, and we're going to return a set as a result. So the things I want to build and the things I need to build those things. Okay? Ingredients. So this is a list of recipes. Questions about this encoding? The fold map ingredients of just says, well, over everything in the set, get the set of dependencies and then combine all of those sets together using a union. Okay, so I've left the ingredients list at the top there just for convenience. That's not normal Haskell notation. Don't get hung up on it. So we can say, given our recipes, I'm also using overloaded lists syntax. So everywhere you see a list, it's actually a set. Don't worry about it. So it's just way more convenient and easy to read. So trace of a set containing string means that I need some wool. Okay? So we're also not keeping string in there because I don't need string to make string. I only need wool to make string. Okay? Our next one, we can actually pass in more than one at once. So we can say, oh, I want to make string and torches. And it will find the things that I need to make either or both of those, rather, and it will combine them all together. And this is a set, so we won't get duplicates in this list, right? It's just a set. Yeah, so you can do that. You just have to choose different monoids. So you could wrap data.map in a specific monoid, which would accumulate the results of that map, and that would do just fine. Cool. So we can switch the notation around a little bit and say we're going to use this ampersand again. So we're going to use this because we're going to start pipelining things, and this is kind of a nice way to do it. So we're going to pass the list of recipes in, and then we're going to trace what we need to make torches. And same thing here, we're going to pass the recipes in to this chain of things that we need. So we can say first, oh, I need string and torches. And then after that, oh, I also needed sticks, but I forgot to tell you. Okay? And because these are sets, and we're tracing, it's going to combine them together implicitly. So when we actually run the function, it's going to start off with the empty set, because that's when we extract, we pass in the empty set. And then, because it prepends, it's going to add on sticks, the set of sticks, and union that with the empty set. Now we need sticks. And then it's going to union that with this set of string and torches. Okay? And so when it combines all of those together, we get the direct dependencies of all of the arguments, and we end up with coal, sticks, wood, and wool. You'll notice sticks is in the result here, because even though it's not a dependency of sticks itself, you do need it to build torches. Okay? This is getting a little bit more complex. Is the example kind of making sense? Great, okay. So we're collecting a set of things that we want to build, and our system is telling us the immediate dependencies. Okay? Cool. And so we have this new function now, which apparently I forgot a slide to introduce. It's called traces. Okay? So what traces does, let's pull up the type signature. That's a good idea. Okay. Sure. So, one second here. Okay. Traces. Great. So, what traces does, this is a mind-bending one, by the way. It takes the output from our traced comonad, or the things that we're computing. So in this case, this is the dependencies that we require to build our recipe. And if you have a function that can convert that back into the input of your function, then what it will do is it will extract your comonad, get the results, and then trace it back into the start again. So what's the intuition here? This is really strange, right? It's like, okay, so if the result of my function can tell me about where I want to move to next, maybe? So we can start to think of things like hill climbing algorithms, right? Where, well, you actually need to look at the results of your function in order to decide where you want to move the next simulation to, okay? And so in this case, we have this dependency tree, and if we want to get all of the transitive dependencies, we need to know which place to go after we've computed the immediate dependencies, okay? So questions about just like kind of the immediate definition here, we're going to see some examples. So this says, given the output, I can map it back into the input. Then I can run it once, run it again after transforming the output, and then get the next output. So it only does it, it runs the comonad twice, once with the original input, or mempty, and then once with the resultant output. This one is a mind bender, and it took me a very long time to come up with an example. Okay, so let's see what it looks like. Great. So the function that I'm using to tell it how to get back to the input is just ID, right? So if we want to keep following the dependencies of our dependencies of our dependencies, it takes a set of things as input, and it outputs a thing of set of things. So I can say, okay, I want you to, remember we're extending, so in every spot of this tree, I want you to look at your dependencies and find their dependencies. Okay? So if we traces, each time we do that, we're going to start off with a quiver. It's going to find its dependencies, which is arrows and a bow. So we have arrows and a bow here. But it also fed those back in, and after it fed them back in, it said, okay, well, what do I need to make arrows? Well, arrows need sticks, feathers, and stone. And so we can see sticks, feathers, and stone. And the same with the bow. We needed string to make the bow. So we've moved 2 steps down our tree. But you'll notice wood is strangely missing. And that's because wood is actually 3 steps down the tree. So each time we call traces, it traces our graph 1 step further. So if we run it again, we can say, oh, follow that graph 1 step further. Now we can see we have basically everything except for coal because we don't have a torch. But we've added wood, we've added wool. It's all there. Kind of cool, a little bit weird, a little bit funky. Any questions on this? So this still matches our intuition of kind of moving around using a monoid. But the way that we're moving is we're climbing through this tree. Now, you'll notice as we descend the tree, we actually still keep everything we've collected along the way. That's because as we do traces, it's going to append onto the existing input, which was where we started. So every layer we go down, we're building up this bigger and bigger and bigger set of dependencies that we need. Cool. All right, so if we just trace quiver, we can see we start at the top, and we get as output arrow and bow. And as we traces it, it will go 1 layer deeper, and we can go 1 layer deeper still. Oh, I just don't have a slide for that one. Awesome. Okay. Whew. I have a tough time believing we don't have at least 1 question after that.
Is there a way without knowing where I want to go?
Mm-hmm.
Trace everything?
You have a very great intuition. Now, if we have something that can kind of, it needs to know the answers of something in order to compute where to go next, and we need to feed that back into the front, that sounds really difficult, right? Anyone have ideas? Fixed point comonads. Wonderful. We're going to get there, I hope. I think we're moving quick enough. We'll probably make it. If not, come see me after. Okay. We can solve that entire dependency tree at once using fixed point over this comonad. It's very cool. Okay. So, in order to get there, I want to get through transformers. Hopefully everybody's not getting too tired out. It's a lot of comonads for one day. Okay. This part, I will warn you, it does get even more abstract. So we're building. I'm hoping that it is mostly understandable, but it's okay if it's not. Maybe look over the slides again, come see me after. We're going to try and keep building so we can get to some cool spots for those who are following along. But I don't want to lose everybody. So, who here has heard of the MTL library monad transformers? Monad transformers in general, yeah? Great. Okay, that's a great spot to start from. So, comonad transformers are effectively the same thing. So the intuition sticks, it's not super reversed or anything. It's mostly the same idea. When you stack monads, you can't do it arbitrarily, but if you know how to stack them properly, you gain the capabilities of each monad in that stack. So if you've got state and reader and accept-t and I/O, then you can use any of the methods from any of those all at once. And they just kind of find where they need to go when they do the right thing. Well, we can do the same thing with comonads. And we can say, oh, I want env, and I want traced, and I want store, and I want to be confused. And you'll get there. But you actually, any of these queries that we've talked about, you can run. And they stack. And it's very strange, because what does it mean to run a query over a structure and have it just kind of find where it needs to go? So let's look at one small-ish example. We now have env-t, the environment transformer comonad. So comonad transformer, rather. And so we still say, it's just like reader, we want settings to be passed into all of our computations. And inside that, we say that we want to stack that on top of a store comonad, which accepts ints. And then we can get a double out from that whole thing. What does this mean? Well, this is just an arbitrary example. So we can now access the interface for any comonad in the stack. So in this case, it means we can use ask or asks or experiment or position or those sorts of things. Great. So here are some examples. Now you've noticed we've redefined these functions to be generic over which exact comonad they're running in. So just like the monad transformer functions, we now have these constraints. And we say, well, I don't care which comonad it is as long as it implements this interface, then we can kind of make it work. So you can actually implement your own versions of these if you want. Just like you can implement, oh, for my appm, I want the state monad or the reader monad or something. Okay, well, monad transformers have lift, why not have lower? First time I saw this, I was like, oh, that's just being clever, right? But it actually turns out it makes sense. When we look at MTL, lift will take a monad and wrap it in some state or lift it into that additional context, right? So when we talk about comonad transformers, well, comonad transformers are all about stripping away state, stripping away context. So if we're given a big stack of comonad transformers, we can tear one of them away and we can end up with a smaller one, okay? And if we keep doing that over and over and over again, we'll end up with just our value. We can strip off the last comonad with extract and end up with an empty value. Or rather, a value on its own, outside of a context. So monad transformers lift and comonad transformers lower. We can peel off the layers one at a time.
So if monad transformers lift is analogous to return for monads,
Yes.
would it be fair to say that for comonad transformers, lower would be analogous to?
Oh, it's very close. So join isn't part of comonads. Anyone want to say what the analogous part of return is in comonad? Extract. Extract. That's right. So here, if we have an envt, so this is the way we define envt. We say, okay, well, we've got some environment. We wrap another comonad, which has some a's inside. Well, we can just put it inside the normal slot here, right? And so if we want to lower it, well, env is easy, right? We just pull it out. But this lower function is exactly equivalent to extract. But for envt, we actually give a different definition of extract so that we can get the A all the way out. But the basic idea is we're tearing off one set of the structure. For store, these types get a little bit crazy, and they seem to maybe not make so much sense. But there's only really so many permutations that you can combine these, and only some of them actually pass all of the laws. So we still have laws when we stack the comonads, they still have to follow them. And so this is the way that you make store T follow the laws. And what it says is, okay, I've got the S that I need, so that I can seek and peek and all that stuff. And I've got another comonad which wraps the getter function. So that means this comonad can actually, as you edit it, it can change the getter function. And in order to unwrap it, well, we say, okay, I want to get this A out of this function. I can pass the S through the comonad. All comonads are functors. And apply the S to this function. So we can fmap this weird dollar thing. It's a little bit mind-bending. The implementations aren't actually so important. So let's keep moving. If you want to see this one, it's in the repo, or you can just look up the source in the Comonad transformer library. Okay, so if we have a stack of comonad transformers, just like with a stack of monad transformers, if you do pure or return, it lifts it all the way up, right? Immediately puts it in the entire thing. You don't have to do lift and lift and lift and lift and lift. Here, extract takes a big stack, and it goes all the way down to a single value. So it does lower and lower and lower and lower, and then extract. Okay? All right, we're ready, I think. Let's see how we do. So we are going to define some Comonad transformer stack called T. There's really no intuition, like there's no business example here. These are just numbers and stuff. We'll get to the actual example soon. But basically we say we have an environment where the environment is this string high, and we can take some monoidal input and sum it with 10. And if we extract, well, we get the, we run extract on environment, which gets out the traced comonad. So sorry, that's lower. So we would implicitly run lower on environment, and then we would run extract on the traced, which passes in the empty value, the identity value, which is 0, which then adds 10. So now we're thinking in layers, okay? If we trace +1 here, it will do the same thing on the environment, throw away the environment, and then it can still run trace on the internal part, and it knows how to do that through that comonad traced constraint. So there's implementations that tell it how to thread this to the right spot in the Comonad library, and it'll trace with 1 and add that to 10, and you get 11. But we can still ask for the environment if we want and just get high. So all of our operations are working harmoniously together. Okay, so now for the example. How are we doing? Oh, we're doing great. Okay, so we want to write a report. Okay, we are business techs, and our business boss has told us we need a business report. So let's do some business. Okay, we're going to use an environment to specify whether our boss wants a very detailed report or just like a summary of kind of how things have been. Okay. So we're going to set up just our outer layer here, and we're going to say, okay, our report is either detailed or summary. That's all we need to know. And let's set up a configuration for this report. So we're going to say, okay, our report config is, it's got an environment, and we're going to say that we want summary report. But then what do we put here? Okay, so we're going to keep nesting, and we're going to keep adding some stuff here. So we're going to fill in this slot. So we've decided we're going to use the traced comonad to say which month the report is for. Okay, this is similar to the function derivative one. You can move forward 1 month or backwards 1 month. You can say, I want next month's report, or I want previous month's report. But the way that we're basically doing this, it's going to start off at month 0, and we can say, okay, I want to get the 6th month's report. But inside the computations themselves, they don't know which month they're at. They just know that they can move forwards or backwards. Okay, so we're going to do some serious business accounting. Say this is our salary or rather our sales projections for the whole year. Okay, based on which month we're in. If we're in, the first month, it's going to be 1.2 to the first times 100. So 1.2 times 100, and away you go. 120 bucks. Not so great. Hopefully we can pay our employees. And if we are in the 3rd month, well, we expect to have grown by then. And so this is just a garbage calculation to give us something fun to play with, yeah? So this, you could pull this data from a database, or you could use actual business projections, doesn't matter. And we can put this traced in here. So the way we wrap env around something is you just put the other comonad inside, and so we've done that. Okay, questions about building this comonad stack here? All good. Okay, so like I said, we can run some queries over this now. So we make sure we use these constraints rather than any concrete comonad types. If we said traced here, we couldn't use it because we don't have a traced. We have an env over traced. So we keep it generic, and we say, if you give me something that can trace over a sum of ints, then I will get a specific value out of my context. This is generic. It doesn't care what the A's are. It doesn't mutate them in any way. It just says, okay, well, whatever we're working with, get me the previous month's version of it. Okay? Or whatever we're working with, get me next month's version of it. That could be salary projections. Maybe it's reports. Maybe it's some other entire thing. Maybe it's stock projections. I don't know. These are generic over the contents. They just move. Okay. So I'm going to define previous month, next month at the top there, just so you can see. And we can start to work with our report config. So we baked in our projections and our environment saying we want a summary report. We can just extract it and say, okay, that's going to say for the 0th month, for the summary report, we've made $100. Okay, not so useful or interesting. But if we extend all of our values into the next month, well, then we can extract next month's projection. So this is equivalent to just saying next month of report config. But it allows us to keep chaining. Yeah. Do you understand that ampersand identifier? So we're basically running this whole chain and then extracting. The way the operator precedence works out is really nice. Okay. Now, this is relative movement, so we can move to the next month, then to the next month, then back a month, and we end up just at next month. So it can still kind of move up and down. Yeah, you had a question? All good?
1% is this like dollar?
It's flip dollar. Yeah. It's in data.function if you want to check it out. Cool. So let's actually do something useful with these projections. So we can look at previous month's projections and next month's projections. We're good business people. We're going to build a detailed report here. So same thing. We're going to say, just give me a traced Comonad, and I will take some float numbers, which are our projections, and I can turn those into a string for you. I can take this whole context and build a string, which is our report. So I'm going to use this weird do notation because things are starting to get a little bit crazy. Hopefully it's not too confusing. Just remember we're passing in a W on the right-hand side every single line, okay? We're passing in our Comonad. So we're going to extract from our current position and get the current sales for whichever month we're calculating. I'm going to look at next month's sales and previous month's sales by looking one forward and one back. Remember, previous month and next month are trace -1 and trace 1, respectively. Then I can build this report and say, well, okay, querying my environment, I've determined that this month's total sales are this, and previous month's sales are this, and next month's sales are that. And we're just going to unlines it into an actual report. Okay, great. So we want a header for our report. I know we're moving through really quickly here. And we can do basically the same thing, except this one has a requirement to look at the environment. So we're going to say, get me which report style we want. Just ask the environment. And then based on that report style, if it's detailed, then we're going to say, oh, here's your detailed report. And if it's a summary report, oh, here's your summary report. Okay? So now, if we build a header for our report config, we baked in that we wanted, I think we baked in that we wanted a summary report, but whichever environment we baked in is what's going to pop up here. This is what happens when you write slides at 3 in the morning. Okay. So now we can combine our header and our report body into one big query. So we're composing queries here, right? Just like you can run kind of monadic operations in other monadic operations, we can run queries inside a query, inside a query. And this weird do notation hack kind of makes it seem natural, which is why I do that. But you can also manually pass the value in and run each of these queries manually, okay? So we're going to get the header for the report by querying for the header of the current report with the current report style. We're going to get the current sales amount. We're going to get the current style. Then we're going to use those, and we're going to say, oh, okay, actually, if the style is just a summary report, I don't really want to do this whole detailed report thing. I want to get the header and then just say, well, we achieved this much sales, this many sales. And if it is detailed, then I'll run the detailed report query. I'll build that thing, and I'll return it and put the header on top. Questions about this huge monolithic thing? Okay, so this is, so this is a semi-group append, and I'm just using this to concatenate all of these strings together. So the header itself has a new line at the end, which is convenient, and then it'll have this as the next line all in one, and we'll see what that looks like when it's printed out. So, okay, so if we print that out, we can say, oh, print this string. If I don't say put str line, it just has new lines in a string, and it's not very pretty, so that's why that's there. And it'll say, okay, if we have our report config, which has detailed baked into it, then it will print out our header, and it'll find the sales for each thing and print them all out together. It's really nice. We can do the same thing. We can say, given our report config, first I want to focus next month before we've done any of the reporting or whatever, and then I want to build the report. And now we have increased our sales. You can see, well, this month's sales are now 120, and previous months are 100. Yeah. And next month's projections are 144. The reason this was 100 here is just the way that our salary projections were. The negative one month was also 100, but that's not important. Okay. Now, we're using this inline local here. We're saying, given a report config, change it to look at next month's reports. Then I want to build a report as though it were a summary report. Okay, so we're changing the environment. We're swapping it out during our pipeline and saying, actually, I want a summary report, build that report, and then extract it. So now it did this very simple summary report for next month.
That means the whole detailed report has been built, right?
Well, so it's all behind functions, right? So it's inside traced. It's all lazy. It'll only build whatever you ask for at the very end. Yeah. So it's moving our position around. It won't compute any of the results until we ask it to. But the intuition is that we're computing it at all places at all times. So that's correct. Yeah.
You need to extract the report on the first example as well.
So if we call a query directly on a context, that is that reduction. It's only after we've extended that we need to have the additional extract. That's right. Very good question. Okay. Let's add one more layer. Do we think we can handle one more layer? Okay. And yeah, we'll see how crazy this gets. Cool. So what if this beautiful report builder caused us to succeed and now we're in multiple countries, okay? And we want to see what our report could possibly be like for each of many countries. So we're going to define just 3 of the regions. We're not global yet, but we're working our way there. We're working in America, and the UK, and Germany. And we've updated our projections. So now we say, well, okay, based on the month and the region, we can say how much we're going to make. So Germany is doing really well. They're going to make a little bit more money than everybody else. Okay? This is just so we can differentiate. Okay. So building your NFT, I'm not going to get into. You can basically just follow the types, and if you get it to work, then you probably did it right. But this is what it looks like. We're going to nest it all in there, and you'll notice we're starting with a detailed report, and we're starting with UK for our store Comonad, which also needs a focus. Okay. So we can now experiment with the idea of what our reports look like in other regions. We've added the store Comonad. That gains us the power of experimentation. Okay? So if we say that our Comonad knows which region we're in and can make computations based on that fact, then we can actually run this experiment over some sort of other thing. In our case, it's regions. So we're going to say, these are all of the regions here. What if, when I'm building my report, I want to make some calculations about the other regions that I'm not focused on? Okay? So to calculate the other regions, given my current region, I just filter the list of all regions. This will give me a list of the other ones. So if I'm in the UK, we'll filter out the UK and we'll just get America and Germany. Now, this is a function from a region to a list of regions. Okay? Remember that experiment, I should have the type signature here, takes a function from its index type into some functor of indexes, and then replaces them all with values. So if we're calculating a report, we can say, okay, well, given the current region, I will find all of the other regions. Experiment will say, okay, sure, I'll find all of the other regions and calculate their reports for you. So it basically just allows us to look at many places at once and shuffle around the results. So here we go. We're going to extract our regular report config, which is the UK on a detailed report. And if we calculate the other versions of our basic report config, which is doing projections, not reports, it will calculate the projections for America and Germany in the first, or in the 0th month, just like that. Does this make sense? This is a weird one. Okay, so this says, I have a query which, whatever is in our Comonad, I want to get out the things that are for the other months other than myself. And it just knows how to do all of that. Okay, so now we can use both store and traced at the same time, and we can build other regions reports for other months. Okay, these capabilities stack on top of each other. So given our report config, we can run it through this other regions thing, and we see, okay, we just get projections for other ones. Well, if we check the other regions first and then project them forwards 3 months, we can get the projections of the 3rd month for the other 2 regions. Or we can do it in the other way around. We're doing this in all places at all times, and the intuition is still, we're not actually running computations, we're moving around a space. So if I move to the 3rd month and then move to America, it's the same as moving to America and then moving 3 months. Okay?
Does it mean that the order of the transformers in this stack doesn't matter?
That probably depends on which transformers. If you're nesting them, I assume that there are some that do matter. In this case, it doesn't. That's a really good question. I should look into that later. Okay. Now, because moving months is commutative, moving 1 month here, or associative, we can move 1 month here, we can move 2 months here, it's the same as moving 3 months at once. We can also split those up and do those in a weird order, okay? We get the same answer. Great. Cool. So, we saw how trace allows us to basically move into other views, but again, every view is kept up to date lazily, right? So it's that intuition that we're moving around positions, and we're not calculating everything all the time, keeping everything up to date. So it's still efficient. Okay, so let's build this comparison report. So I'm going to pass in this W explicitly here, and I'm going to say that all of the other reports for other countries we can get by generating the same detailed report query over the other regions. So we're generating all reports for all regions, and then, we're generating a report for our current region, and then moving to the reports for other regions, and collecting those as a list. This is trippy stuff. Then we can get them out. We know that each of these reports is a string, and so when we experiment, we get a list of the strings. So now we have a list of all of the reports for other regions in whatever our month is. Then we can stack those other reports for each region by unlining, so it just puts a new line in between each report. And we can say this is our comparison report with a header. Questions on this one? Okay, we're starting to lose people. Okay, this is getting tricky. That's totally fair. Let's look at some examples and then maybe, yeah, we're almost done here. So, yeah. Oh, we got a question, yeah? Okay.
I've got an unrelated question.
Yeah. Just gonna see how much we.
Comonads related to lenses, if at all.
So there's not really any implicit relation. So monads aren't really related to lenses either. You can use one and the other. There are certain lenses which operate over comonads. There's some lenses in the comonads library, but in general, there's not really a strong relation. That's been discovered yet. So good luck. Maybe you can. Okay. So here's what happens when we print out a report. So we're still saying we want to do the original report over the next and previous months. But we've also calculated, this is the comparison report. So we're focused on UK. It has generated a report for America and Germany in the next and previous months. Just like that. And if we want to generate a full report that also contains the UK, this comparison report is a query. We can run it inside our other queries. So just like you can run a monad in other monads, you can run a query inside other queries. They all stack really nicely, and we can pass the W in implicitly, run our comparison report, and then combine it with our regular report, just like we did before. That's all the same code. we're just adding the comparison report. Now, when we build our report for our report config, we get a detailed report for the UK and comparisons for other countries, other regions. And we can do the same 3 months in the future. Good stuff. And if we want, actually, so this is to emphasize that we're just moving around a space. If we build up this new context by saying, oh, for my current report config, build a report, it's going to build that huge multi-country whatever comparison report. Even after I've done that, I can say, oh, actually, I meant to look at Germany's. Go move to Germany's. And now, even though we've already finished the whole pipeline, we say, oh, I actually want Germany's report. Oh, here's Germany's report. Here are its other regions. And it'll just do all of that for us. Cool. So again, we've got monthly reports. We can build them like that. If we have the monthly reports already, we can just peek at Germany to get Germany's report. We can keep going and say I want Germany's March report. Or I can say I want all February reports by experimenting over all regions 2 months in the future. So here we're not doing that weird filter thing. We're just going to say whatever country I'm on, I don't care. I actually want to look at all countries. That's it. So that's Comonad transformers. All of these slides will be posted. I think they're already on the repo. There's some PDFs there. You can go digging through them at your leisure. All of the code for all of this stuff is also in that repo. You might have to go digging around a little bit, but it's in there. Yeah, this has been Comonads with Chris. Thanks for coming out. We do have 4 more minutes, so we got a request. Let's do it. Okay, real quick. But there are full slides for CoFree, for zippers, for fixed point Comonads, all in the repo that we just didn't have time to get to. So the fixed point ones are really interesting. I recommend them. Okay, but we wouldn't have time to do that now. So CoFree. What's a CoFree Comonad? This is going to be crazy fast. Woo! Okay, so sorry about, I'm going to apologize for what I'm about to do. Okay, so if you are already familiar with free monads, they give you a monad for any possible functor. A co-free comonad gives you a comonad for any functor at all. So if you have a functor in mind, you can inject it into this structure and it will generate a comonad. What that comonad does depends on the functor, but it's a little bit tricky to say. But they'll have some behavior and it will be a comonad, I guarantee it. So this is what it looks like. We have a value at the top and then a tree based on the functor of all values and trees and values and trees and values and trees. You can model almost any tree using these co-free comonads. So let's look at some that we've seen. Stream is the co-free tree over identity. It says I have an A and I have another A and I have another A and I have another A all the way down. And so you can see kind of a relationship there. They're all wrapped in this identity functor. Great, thanks. So when we're constructing co-free trees, this is kind of annoying, right? It's in an infinite, never-ending tree. There's this function called coiter, where if we give it a coalgebra, which says given an A, I can generate the next iteration inside a functor, then we can generate this whole tree, and it'll just keep iterating, iterating, iterating. This is very similar to the ANA from recursion schemes. It's basically the same. And actually there are recursion schemes instances for all of CoFree, so go have fun. So if we want, we can build count like that by using the coalgebra that just adds 1 to each for the next identity. And it will build out a never-ending stream counting from 1, 2, 3, 4, 5, 6, 7, 8, 9. There's also this unfold one, which is just a generalized version of that, where we can separate the seed type from the actual value type. That's kind of cool. What does this type look like? Anyone have a guess? It's a list. Very good. It's a non-empty list, more specifically, because it's a comonad. It must always have a value. There's a value at the front, and then maybe we have another value, and then maybe we have another value, and then maybe we have another one. So the list could end at any time. Okay, that's great. We can make an alphabet. Don't have time for that. We've got a tree. Okay, how do we represent a normal rows tree using a co-free comonad? So this is a tree that has a value at a node and any number of children. List. So if we pass this structure a list, it will say, well, I have a starting value, and then I have all of these children. This gets really tricky to write out, but the intuition is still there. We can build this tree. Okay. Cofree actually is a variant of fix, which is why we can have these nested recursive structures without having problems at the type level. But it's a version of fix which has a product at every layer. So that's kind of the intuition there. We can also thread monads through here. So this is also very similar to Paul's stuff, where basically we can unfold and have a monad constraint. So we can crawl a file system using I/O and then build up a file tree. So a file tree is just a rows tree of files. Cool. Okay. Any ideas what this one is? So it's a const functor, which means it has how many elements inside it? Well, 0 A's, so that's just env. Oh, sorry, it has exactly 1 A because it always has the root of the list, sorry, but no children, so that's actually just env. And we can build store, if we're ambitious, by composing functors, where we compose this getter function with a tuple of its argument. Okay, so at every layer, we've got a tuple of its argument, and we can pass it into the S, and if we go into that infinite amount of children, it's the same as extending. So each layer we go down, it has moved all of its children by the value that we passed in. Okay, it's time to be done, unfortunately. There's not that much left. Okay, I got 2 more. Okay. So the traced comonad is the same. We can represent it as a function from M, and if that M is a monoid, then this is the traced comonad. And we can also perform natural transformations over cofrees, which is kind of just handy in certain cases. Cool. We're not going to move on. Okay. Cool. Thanks for coming. If you're interested at all in the stuff that we went over, I've got a blog here at chrispenner.ca, and I try to teach complicated things in slightly less complicated ways. I've also got a Patreon for that blog, so I'd love it if you could buy me a coffee for a post or whatever. And I plan to actually start writing a book on lenses very soon. So if you want to support me while I'm doing that, then I'll probably have some Patreon, like support me and get the chapters as they come out sort of deal. That'd be sweet. You can find the Patreon at any post at chrispenner.ca. I've got my GitHub and my Twitter there. Come talk to me after. This has been great. Happy Monadic Party.